All right. So this first couple pages in this notes, if you turn the page, you'll notice that we don't actually get started with math until the next page. But I usually like to start by just thinking a little bit about, like, what are we going to look at in this course? What's the point of taking this class in general? And, it's the kind of thing that I hope sets the stage for the class, but also the kind of thing that once we start looking at material, and if things are kind of feeling like your head's spinning or something, you can come back to this and think, like, what are we doing again? What is the point? And hopefully that'll help guide you back into the right mindset. So, sorry, let me just get my note out here. So there's basically, as I think about it, two ways to think about a phenomenon. And when I say phenomenon, I mean something related to your own major. Right? A lot of people in this class end up being like bio majors, or maybe you're in business or physics or some other major, and you want to think about something in your own major, whatever that is. Can I just ask too, before we get too far, is it like super choppy? Are you able to hear me okay? I just worry about my internet connection sometimes.
I can hear you fine.
Everyone's okay, and I move my
pen around. You're good.
Okay, cool. Thank you. I think once we get started, it'll be a little more natural. I just want to make sure everyone's good. Okay, everyone can hear. Great. So anyway, when I say like some phenomena, think about something in your own major. Like if you're a business major, maybe you care about the stock market or profits or something, or if you're in biology, you care about some population that you want to grow, right? Something you're interested in. There's two ways to think about whatever it is that's in your brain right now that interests you. You can think about it quantitatively or qualitatively. Right. And a lot of times in many majors, we think about things qualitatively. We make observations, we describe things using words. When I think about this in a science class, I think about someone out, taking notes in the woods of some population or something, right? So you write things down. But in math, a lot of the time, we think about things quantitatively. And it's not just math. There's certainly lots of other quantitative things in all other majors, and that's a lot of the times why people are in this course, because you want to have some kind of quantitative basis to help you with your own major, right? And so it's quantitatively, it's more about using numbers in our data and thinking about functions and math, right? And so in calculus, we're going to think about things from that point of view, right? From the quantitative point of view. And usually, once we have enough information about something, we create a mathematical model about it. And so in this class, I always come back to mathematical models that describe situations. So for example, it could be a population model or a profits model or something that we really care about, right? Some function that describes something we care about. Now, to sort of define that a little more, it says what a model is in detail right here. A mathematical model is a description of a system using mathematical concepts and language. And most of the time, especially in this class, we're going to be thinking about models that are functions. Okay? Now, a function, if you remember back to your pre-calc, some of you guys, I was just teaching functions, what a function was in my pre-calc class. A function is a rule that assigns to each element, x, which comes from the domain, exactly one element, f of x, which is in the range, right? And so it's like we plug things into them. Most of the time we think about those as x values, and something comes out. Most of the time we think about those as y values, right? So these range are oftentimes y values. And again, the functions we're going to be thinking about in this class are going to have, most of the time, trying to make them have some kind of hypothetical meaning. Sometimes they're actually real functions, but at least we'll be thinking about them hypothetically as something we care about. Again, right? Think about profits or some population or disease spread or something like that. But before we kind of start using functions, let's just remind ourselves exactly what they are. So I love these little like TV-looking boxes or whatever that oftentimes people use to represent functions. So let's look at a real simple function. Right? F of x equals 2x plus 3. This function is a straight line, right? When you plug an x into it, you multiply it by 2, and then you add 3 to that result, and then that becomes the output, right? And so you can certainly plug numbers or letters or anything you want into the function, right? And so if this is our function f, inside the box, you take x values from the domain, right? You stick them into f. Something happens to them. In this case, multiply by 2, add 3. And what comes out is the output value. And that's going to be in the range. Right? And again, you can kind of think about this as like, obviously x is an x value, but the thing I want to clarify, sometimes people get confused about what f of x is. F of x is a y value, right? It's an output. So even though it says, f of x, so it looks like there's an x in it, it's really a y value. It's the function value when you plug x in, right? And so really simply, if you plug the number 2, and you plugged it into the function 2x plus 3, right? Multiplies by 2, adds 3, and a 7 comes out. Very, very straightforward. And again, if this is something we cared about, maybe it's like after 2 years, there's going to be 7 animals or something like that. But the point is you plugged an x in and you got a y out, right? And the thing we learned about in pre-calculus that I'll just kind of remind you is the definition of a function means there's only one thing that comes out. You can't have 2 things come out. It's got to be just 7 that comes out when you plug a 2 in. Right? That's the only thing that can produce a 7. That's sort of the general idea. But again, you can plug like anything you want into them. Right? You can plug the number pi in. Right? If you plugged a pi into the function 2x plus 3, it would become 2 pi plus 3. Oops, that should be a pi. And we could get an approximation for that if we wanted to. But I'm just trying to point out that we can plug any kind of number into them. Or the thing we also looked at in pre-calc is you can plug other variables into them, right? So you could plug like a plus h into this function. Right? We looked at that in pre-calc. And that would look like this. And we'll look more at that later. I know we looked at that in pre-calc, but that's something that's going to come into play in calculus as well. So again, just kind of thinking about reminding you what a function is and previewing how we're going to use it. And when you think about sort of collecting up all the possible outputs, that creates the graph. Right? So the graph of a function, if we're actually going to write down what it looked like, that would be all the ordered pairs that are of the form input output, right? So like this is just a straight line. So if we were going to graph that function, it would be very easy to do. It's got a y-intercept of 3. It's got a slope of 2, and so it would be something like that. But what I'm trying to say is, and the thing that sometimes people forget or lose sight of, is when you write down a graph like that and you write the line, it's just collecting up all these possible outputs and just plotting them and connecting the dots, right? It's one way to think about that. All right. Thoughts about that so far? Questions there at all? Okay. Alrighty. So, what do we do with functions? Well, here's a couple hypothetical scenarios that we'll look at kind of similar functions to these throughout the course. So I'm going to think about 3 hypothetical functions. One's going to be q, one's going to be g, one's going to be w. And then we'll think about the kinds of things we can do with those functions. So let's say q of t represents the quantity, so that's where q comes from, of some drug in the bloodstream t minutes after taking it. So let's say you take some Advil. It takes a while to start working in your body, and q tells you how much has actually been absorbed after some amount of time. Let's let g of o be the price of gas given the current oil price. Right? So we want to know how much we're going to have to pay for gas. Well, that depends on the oil price. And so G of O would tell us gas price depending on how much oil is. And let's let W of R be the number of wolves in a forest depending on the number of rabbits that exist, right? Because so wolves eat rabbits. The more rabbits there are, the more wolves there are. And so that depends on W depends on R. So one kind of question that we might care about is something that happens at some specific point of time, right? Knowing what happens at a point of interest. So for example, using the drug example I just said, you've got a real bad headache, you just took some Advil. How long is it going to take to work, right? And so you might want to know, like, I took Advil 30 minutes ago. You might want to know how much is in my bloodstream now. How long is it going to take to work? And, that's something doctors really care about. If someone's in the hospital and they want to know when their drug that they gave them is going to start to work, they have some functions that tell them that. It usually depends on things like body weight and maybe metabolism, things like that. But the thing I'm trying to point out here is this is at some specific point of time, right? At 30 minutes, when what's going on. That's different than this next question, which is what happens way down the line in the long run. So, for example, let's think about the wolf example, we might want to know how many wolves could possibly ever exist. So how many wolves could there ever be out there? And so if wolves are a function of rabbits, we would want to make rabbits really, really big and see how many wolves could respond from that, right? And so just to kind of think about how we would answer these first two questions, because these two questions are kind of similar to each other. Let me actually ask you guys, if we had a function that told us Q of t, you plug in t and it tells you the quantity of some drug, in this case Advil, in your bloodstream. If we wanted to know, if we had that function and we wanted to know how much Advil was in there 30 minutes later, what would we do practically? What would be the operation we did? Thoughts? We have some function, it tells us the quantity. We want to know what it is at 30. What would we do?
Set t to 30.
Yeah, just plug in t of 30, right? So let t equal 30. Just plug it in to q, right? That would tell us exactly what we wanted to know. And thinking about how many wolves could possibly exist, we would want to let the rabbits go to infinity. So this is some notation we'll see. You can actually see it right down to the bottom of the page here. We'll see that notation in just a second. This means let R get really big. Let the number of rabbits go to infinity. And so to kind of summarize those two things, both of these kind of questions are limit questions. And so that's the first thing we're going to learn. You can see that's literally the next topic at the bottom of the page here, limits and continuity, chapter 1, right? And so limit questions sort of help us think about either what's happening at a specific point or what happens in the long run, right? Those are limit type questions. Now, eventually, what we end up doing after we understand limits in the first chapter or two is we use that to build towards other things, like these two other examples. So the third one says, both of the previous things can be posed as rate of change questions. So, for example, we might be in some industry that really depends on gas. Like, let's say we have a bunch of trucks that are in our business and we fill them up with gas all the time, right? So it's important for us to know how the price of gas is changing. Is it getting more expensive or less expensive over time? Because if you need to fill up 100 trucks with gas and the price is going up, you would want to fill them up like right away. But if the price is going down, maybe you would want to wait a little bit to fill them up because you'll end up saving money. So you might want to, if you really care about gas in your industry, you would want to know how it's changing, right? And so we think about how things are changing using derivatives. And so that's going to be the next chapter. So I don't know, I can't remember if it's chapter 2 or not, but the second part of the course tells us about derivatives. And we use limits to derive limits, derive derivatives. That's unfortunate that derive and derivatives kind of look the same, but limits sort of lead us to derivatives is one way to say that. And then the last thing we're going to study is how we sort of think about total amounts. So an example of total amounts that we might be interested in is like, well, let's say over the course of an entire day, we took Advil, how much was absorbed by our body over the entire day or something like that, right? So like how much, I should say. Let me just wipe that out. How much Advil is absorbed by the body over, say, a 24-hour period. Right? That's different than the first question we thought about, which is what's happening at 30 minutes. That's saying like, well, over an entire day, how would that work, right? And so we would answer a question like that using integrals. And so that's the last thing we look at. And also, so this is like end of Calc 1 is integrals. If you're going to keep going into Calc 2 really starts getting into integrals. So we kind of usually introduce the idea of integrals in Calc 1, and then it really gets explored in depth in Calc 2. So the first chapter in the text here in our course is about limits. And as I mentioned, we did this kind of overview last class talking about the types of things you might see in the course. And limits is the first thing, and we use that to build derivatives and integrals. So limits are, a foundational thing here, and oftentimes the most confusing thing about limits, in my opinion, is the notation. And so this is the notation I want to kind of focus in on right away. Right? And so this lim with this x arrow a, that's taking a limit of this function, and it's saying that that equals L. And so how do we actually read that statement? That's an important thing to know. This statement reads, the limit of the function f of x as x approaches a is L, right? So that's how we would read the left-hand side, and then is L is the equal L thing. And so what that means is x values, which are the things you plug into the function, obviously, right? Those things are getting closer to the number a. And so this is saying when you plug in x values close to the number a, the output is near L. And if that's the case, we say the limit is L. Now this exists, so this word exists implies that sometimes it doesn't exist, right? So it only exists, the limit does, excuse me, let me let this person in. The limit only exists if the function, like I said, gets arbitrarily close to L as x gets close to a. So let's just draw a quick picture here that maybe can help us think about this a little better. Let's say we had a function and it looked like this. Let's just say it was some exponential function like, I don't know, e to the x. And let's say the value, the a value we care about is right here, right? So a is some number on the x-axis. And the idea, what this is telling us is, it's telling us that as x values get close to a, the output should get close to L. Okay, so L you can see is a y value, in other words, right? It's a function output, that's the L value. And a would be the x value. So what the definition is telling us is if we walk towards a from this side or from this side, in either case, the function is both approaching L from both sides. You see that? And so that's what the next line is telling us here. It's telling us that the limit exists. Let me go ahead and box it in red. You might want to box this in as well or highlight it or something. This is an important thing that we're going to want to work with throughout this entire section, and really the rest of the course, is the limit that we care about, this limit as x approaches a, exists if and only if these two things are both true. And so the first thing I'd like to sort of ask you to think about is, what is the difference? It kind of looks like it's just saying the same thing 3 times, right? What's the difference between this thing on the left and these two things, right? What do these two things on the right have that this one on the left doesn't have? What's the added notation? Anyone?
The negative and positive sign.
I'm sorry, could you say that again? Someone said something, but I couldn't hear it.
The negative and the positive signs?
Yeah, the negative and the positive signs. I thought I heard someone send a message to, yeah, there's a message that popped up as well. The plus and the minus, yeah, exactly. So this part is the added part. Maybe let me circle it in another color here. right? The bottom part here has a plus next to the A, and the bottom part here has a minus next to the A. And so that plus and that minus are an added instruction, and that added instruction could be read as X approaches A, and then the plus sign means from the positive direction or from the right side. The right or the positive direction. So that part there, the plus part, is this part right here, right? This is walking towards the function from the positive right direction. So the thing I'm pointing to on the graph is the plus side, right? This is like coming from the plus. And then the minus side, what color I should use? Let me switch back to red. The minus sign would be from the negative direction, right? So this would be as, not as, but as X approaches A from the left or negative direction. Right, so that's why it's a minus, because it's like from the negative side, right? So that would be this left side, right? That's the minus side. So I'm going to let everyone just kind of catch up and write that down, but I'm going to just try to repeat that one more time and see if I can clarify something. So I will repeat that one more time. Just give everyone a second to catch up. Questions? Let me also ask well, let me see if there's questions so far before I say something. Go ahead. Can I ask you, I've got my, let me ask you a fundamental question here. I've got the Google Meet up on my computer, and then I have it also up on my iPad, sort of trying to monitor what it looks like. And on my computer, it looks very crisp and clear, but then on my iPad, it feels kind of blurry. And I'm wondering if it's my internet. Can you give me some feedback of does it look blurry to you on the screen right now? Anyone?
It's a little blurry.
Someone says it looks okay, a little bit blurry.
Yeah,
Okay.
I'm on a computer and it's a little bit blurry.
It just went in and out of focus, so I don't know if it's your document scanner.
It seems like it might be computer specific, because I'm on a Mac. On my Mac, it looks blurry, but on my PC, it actually looks quite clear. So I've been thinking, someone just said it's good now, readable. That doesn't sound great. I've been thinking a little bit about switching to using my iPad. That would be quite clear. Let me review some of these videos and I'll have to make a decision. I might just switch in and out. My original goal, I wanted to use Zoom. I was going to switch over to Zoom, but when I actually tried to use my document camera on Zoom, for whatever reason, it was super, super blurry on Zoom. I have no idea why. I spent like half a day. I wasted half a day of my life trying to get this to work on Zoom, and I just couldn't. So I switched back over to Google Meet. Google Meet also seems a little bit blurry. Anyway, I might switch over to my iPad soon. I wanted to do the document camera because if we're going to be in person, it's easier to do the document camera in person. So anyway, I'll have to figure something out. I'll think about this. I'm going to stick with this for right now, but just know I'm working on it. So let me repeat what's going on here. So we're trying to think about the limit as x approaches a number of a function. And what we're saying is that exists if and only if both the left and the right-hand limit both equal the same number, right? So that's a very key thing. See how the L is here, and it's also here, and it's also here. And so we need the limit from both sides to equal the same thing. And so if I'm looking at that sort of arbitrary, easy picture, the idea is when I walk along this function from both sides, it approaches the same point, right? And so that's why in this example right here, the limit does exist. But that's not always the case. And we'll look at some examples where they don't always approach the same number, or they might approach the same number, but there might be a hole there. And so the limit might exist, but the function might not be defined there. And so there's all these sort of special cases, but just trying to lay out the basic idea first. We're obviously going to look at this example here. Can I clarify something before we look at this example? Questions? All right, so I'm going to keep going. So let's we're going to look at this one in a couple different ways here, right? So we're going to look at the function sine x over x. So that's kind of a funky looking thing. Let me go ahead and just draw the picture right here. I would suggest you draw a small-ish picture right here, and then we're going to fill up the rest of this looking with that. So if this is sort of the x and the y-axis, then that function kind of looks like it does like increasing bumps. And then it does this, and then there's a hole right here. And then it does the same thing on the other side. And it kind of keeps going. And there's a hole at 0. And there's a hole at 0 because you can't plug in 0, right? If you plug in 0, you end up dividing by 0. So there's a hole there. So that's what the function looks like. Sine x over x looks like that. And if you look at the two limits, we're going to look at the limit as the function approaches 1, and then the limit as the function approaches 0. And so 0 is where the hole is, right? And 1 is like, I remind myself where 1 is. 1 is approximately like right here. Right? And obviously 0 is right here. So if we're approaching 1 on this graph, 1 is the easy part because there's no hole there. We would want to think about walking along the graph in either direction approaching 1, right? So if you approach it from the right side, you're kind of bumping along here, and you're going to approach this point right here. Right? This is kind of where the function value is. And so it's defined at that point, and if you approach the value of 1 from both sides, the graph is approaching the same location, right? You see that? And moreover, you can actually plug a 1 right into the function and get a value out, right? So if this is our function, notice how if you just plug a 1 in, that's fine. You can do that, right? You would just do like sine of 1 over 1. Sine of 1 is a value. It's not one of the ones, if you're coming from my pre-calc class, it's not one of the ones we know off the top of our head, but we could use a calculator and get that value. It turns out it's 0.841. And so it turns out at this point, it actually has a value. And so if you can plug a number in to the function, then the limit exists at that point, and it equals whatever that value is. And so in general, sorry, someone's trying to get in here. So in general, if a function is defined at x equals a, then the limit of that function is just what you get when you plug the number in. There are kind of a couple small cases there, but that is generally true, where if you can plug the number into a function, then the limit exists there, and it is what it is. But you can't always plug numbers in, right? So we already said, like, if we looked at this graph here, let me try boxing it in. It's starting to get crowded in here. There's a hole at 0. So if we wanted to look at the second limit at 0, you can't actually plug that value in. Right? So, and I want to be very clear about that. You should always try to plug the value in. But notice on this one, if you try to plug 0 in, you get sine of 0 over 0. That's a problem because sine of 0 is also 0. So you get 0 over 0. This is undefined or also known as an indeterminate form. And so that's no good. We can't just plug 0 in. But if we look at the graph, the limit does exist. And I think that's very key to keep in mind. You can't plug 0 into this function because you divide by 0, right? You end up with 0 over 0. But if we kind of look at the graph and we just approach the point 0 from both sides on the function, you're kind of walking up that middle hump there, and you're approaching the same point at both locations. It's just you can't plug that point in, right? So the limit exists, but we can't just plug that number in. And so what I'm trying to say here, it looks like the limit exists, but we need a better way to figure out how to deal with these things. So it looks like the limit exists, but we need some tools to estimate the limit. So my general goal on this page is sort of to have introduced what a limit is, show you two where they exist on this simple graph, but kind of show you that, hey, you can't always just plug the number in like we could in this first one. And so if you try to plug the number in and you get some weird thing like dividing by 0, we need some better tools. And that's what's on the next page, right? So if you turn the page, it says 2 ways to estimate limits. I'm going to pause here, see if I can clarify something. Thoughts? All right, so there's 2 ways to estimate limits on the next page. And estimate is the key word on this page. We're just trying to estimate them, right? We're not necessarily calculating them exactly on this page. If you look 2 pages from now, we'll look at finding limits analytically, which means getting an exact value. But to kind of keep driving the point home about what a limit is, and to give you some tools to start thinking about to estimate them, let's look at a couple examples. So one way we'll look at, and then at the bottom of the page, I'm going to try to split folks up. I'm going to do my first ever breakout room thing where I'm going to ask you to think about this one in groups. So focus in here because I'm going to ask you to think about this one with a few classmates in just a second. So the 2 sort of ways we'll think about estimating limits is going to be graphically. So just looking at a graph, that's always really nice to do if you have a graphing calculator or something, or you can create a table of values. And again, these are ways to estimate limits, not necessarily get them exactly. So it's like worst case scenario, we can always do this thing if we can't figure it out. And let's look back at that same example. So let's look at the limit as x goes to 0 of sine x over x.
Hey, Professor, you mind if you just drag that down a little bit? All right, thank you.
Yeah, thank you for that. If I ever run off the page here, I'm trying to manage a lot of different screens here at one time. So just let me know if I mess that up. I'm actually just going to graph this thing too real quick because I wasn't sure I had the right graph. Yeah, it's a little bit. Let me see here. I think it might actually go below the x-axis, so I just want to make sure I have the plot right. Yeah, okay. So let's graph it again, and I'm going to draw a more careful graph this time. The graph looks more like something like this. And it goes like this. There's that hole. And it does this. So it does go below the x-axis. And that hole, if you kind of look at the picture, it's approximately at 1. Y equals 1. right? So I'm literally just pulling it up on my computer. I'm using wolframalpha.com just to plot this thing and see what it looks like. And it looks like that. And so if you have a nice graphing calculator or a nice tool, some way to graph it, you can just kind of look at the picture if you have a careful enough picture and see what the limit is, right? And so just to be clear, the limit as x approaches 0 from the left of this function is walking along this way towards the number 1. And I see that as I do that, I'm getting closer and closer to the number 1. And then from the other side would be doing it over here. The limit as x approaches 0 from the right is doing the same thing, but you're doing it over from the positive side. And in both cases, you're walking up that hump towards the same point. Okay, so since the left-hand limit and the right-hand limit are both the same thing, the definition on the last page is telling us that the limit exists, right? We have both these left-hand and the right-hand limits actually equal the same thing on the last page. And so that means the limit exists and it equals L. And man, it looks so crisp on my one computer and it looks blurry as heck on the other one. So sorry if it looks blurry. I'll review the video and make a decision there. But anyway, based on this picture, what we can conclude is that the limit as x approaches 0 of this function is 1. It's an estimate because we're just kind of looking at a picture. We're not like doing something real carefully. But it looks like that's going to happen. By this point, we've drawn this picture a couple times, and I'm trying to be clear about what the left-hand and the right-hand limit are. It should be sort of kind of clear what that means. Are there questions about what it means to do the right-hand or the left-hand limit notation-wise or walking along that function? Anything I've just said? See some folks write in. I'm just going to pause 1 second. All right, if we're going to do a table of values, we need to do the same thing. We need to do the left hand and the right side limit, but we need to plug numbers in. So I'm going to approach 0 from the left in this table, and I'm going to approach 0 from the right in this table. And so these are my x values, and this is going to be my output. And I just used a calculator to do this. I just plug numbers in. And so if I'm plugging numbers in to the left of 0, they're going to be negative, right? So it's going to be like minus 0.1, minus 0.01, minus 0.001, right? These are numbers that are getting closer to 0 from the negative direction. And then I'll do the same thing. I'll plug the same numbers in, but the positive versions. Right? I'm approaching 0 from the left and the right in this table. And I'm just going to plug them into the function. Again, I did this on my calculator ahead of time. I just kind of plugged each one of these x values into that function, and I got the following. When you plug 0.1 in, you get 0.9983. When you point 0.01 in, you get 0.999998, and then 99999 repeating, right? And so you can see these numbers are getting closer and closer to 1. All right, these numbers are approaching 0 from the left. And the same thing happens when you approach from the right. You get numbers that approach 1, literally the same numbers, 0.9983, 0.99998, and then just a bunch of 9s repeating. All right, so these numbers are approaching from the right. And in both cases, they're both getting closer and closer to the number 1, right? These add 0.999, you keep adding 9s on, eventually you're going to get closer and closer and closer to 1. So kind of, based on these two tables, I see that the left-hand limit and the right-hand limit are the same. And so that means the limit itself exists and equals 1. Allow me to pause. thoughts at all? Any questions so far? Look, you can see at the bottom of this page here, I'm going to ask you to try this with another function. Well, hopefully in groups. And, you know, I'm not necessarily going to ask you to do this. You may not get super far, but I'm hoping this will give you a chance to maybe clarify with smaller groups. I know sometimes it's hard to like jump out in front of a class and ask a question. So maybe in a smaller group, you can say like, hey, what was he saying about that? And maybe someone can help. But my hope is at least you can set up the idea for this next problem in a group, and then we can go through it together. So again, I'm going to just pause and see if there are questions about this first one before I set up the next one. And I'm going to give this, I'm going to try breakout rooms, see how that goes. Questions? Can you record through breakout rooms? I don't know. We'll find out. All right, I'm not really hearing anything or seeing any chat. So on this particular one, there's a hole at x equals 2, it turns out. But when you look at the graph, it kind of looks like this value down here is near y equals 1. And when you plug numbers in from the left and the right, you should be able to verify that. And so when you plug numbers in from the negative direction, that looks like this, right? So this is x approaching 2 from the negative side. And this one is x approaching 2 from the positive side, right? So we're plugging in numbers a little bit less than 2 here, a little bit bigger than 2. And when I did that on a calculator, I got this. Oh, no, that is negative. So that should be a -1, sorry. 9.09. I got -0.9901, -0.999. And so it looks like the numbers are approaching -1. And the same thing happens when you do it from the right side. And again, I just plugged these x values into the function f of x and got these numbers. And so the graph kind of confirms, oh yeah, it does look like those numbers are near -1. When I plug in values, it looks like they're approaching -1. And so just to be clear, sometimes it's not clear. Like we're thinking about the number 2, right? And so these values are approaching 2 from the left, and these values are approaching 2 from the right. So anyway, it looks like both of them are equal on both sides. And so my final answer here is the limit as x approaches 2 from the left of this function is the same thing as the limit as x approaches 2 from the right. And in both cases, it equals -1. And so that implies that the limit itself exists and equals -1. This is sort of like the final answer. Everything above there is kind of exploring this idea, trying to reach that point. Questions?
When trying to find that answer, we only looked at the left graph, right? The left L-shaped.
Yeah, that's
graph.
right. Because we were focusing on x equals 2, and that was only on this left-hand graph. Yeah, the graph itself has 2 pieces, but we were focusing in right around 2.
Sure, thanks.
Other thoughts?
I got a question.
Yeah.
How do you find the hole? I seem to be confused on how you find the hole.
So it has a hole. Maybe I should have just done that here too, because if you try to plug a 2 in here, is this on the screen? Yeah. So if I try to plug a 2 into this function, you get a 0 on the top, and then you end up with 4. You end up with a 0 on the bottom, right? You'll get 4 minus 10 plus 6. Anyway, you'll get a 0. Right? And so you can't just plug a 2 into it. That's an indication there's a hole in the graph there. I know it doesn't look like there's a hole on the picture because it's just one small little point, so it's not like highlighting it. But you can see there's a hole because you can't plug a 2 into it.
Okay, that makes sense.
Other thoughts? I just want to finish with the next page because I hope the next page will illustrate cases where limits don't exist, where that's the whole point of the next page. And so that, I think, should clarify some things if people are still very confused. And so I want to do that in the next couple minutes here, just before we spend the last part of class submitting something. And so if things are not clear about limits, I'm hoping this page will help with that a little bit. I meant to pin this up here, though. Okay. All right. So this page, as you can see at the top, it's all about limits when limits don't exist. And I oftentimes abbreviate does not exist with just DNE. Just be aware of that. So a limit doesn't exist when one of these three things happen. So the first thing that might happen is the function approaches different values at either side of the place you care about. So like on this first one. So this first one is an example of number 1. Absolute value of x over x as we approach 0. So let me graph that for you. That looks like this. On the left-hand side, it's down at -1. On the right-hand side, it's up at +1. And there's nothing at 0 because you'll divide by 0 if you plug it in there, right? So the absolute value, you're basically dividing x by itself. So you're always going to get the number 1. But if it's a negative number, you have a negative in the bottom. And so that's why it's down here at -1. But if it's all positive, it's going to be a +1, right? So that's what that graph ends up looking like. Now, when I walk along this graph, if I approach from the left here, let's look at the limit as x approaches 0 from the left. That's down on this graph right here, right? I would be walking along this graph, and I'm just at the number -1. But if I walk along the graph from the right-hand side, I'm up on this piece, and I would be going this way, and I would be up at +1. Right? So that's this direction compared to that direction. And so the left-hand limit and the right-hand limit both exist, right? They're both approaching something. This one's approaching -1. This one's approaching +1. They're just not the same thing. And so kind of the take-home of this first one is that the limit as we approach 0 from the right is 1, which is not the same thing as we get when we approach 0 from the left, which is -1. And so since they're not the same, the limit doesn't exist. All right, this is kind of like the point that I'm trying to make here. And it only happens at 0, right? 0 is the problem there because the graph like jumps at 0. Thoughts about that? You see why the limit does not exist at 0 here? The second thing that might happen, number 2, is the function might grow without upper or lower bound at that point. So the second one is an example of number 2. Let me go ahead and graph that graph for you. It turns out there's an asymptote at x equals 1. So think back to some of your pre-calc stuff. This is what I do, at least at the end of pre-calc, because we talk about asymptotes, right? There's a 0 in the bottom at x equals 1. That means there's a vertical asymptote there. And so the graph ends up looking like this. It like explodes up to infinity at that point from either side. That's what I get when I plot that. And so as x approaches 1 from the left, you're walking along the left hand of the graph, and it's shooting up to infinity, right? It's not getting closer to something. It's just getting bigger and bigger and bigger, and it's going to keep doing that all the way up to infinity, right? And the same thing from the right. It's just exploding up to infinity. And so what we would say here, right on the right here, since the function 1 over x minus 1 squared grows without bound at x equals 1, the limit as x approaches 1 doesn't exist. The function needs to be getting close to something near that number, and we can see just looking at the graph, the graph is just getting bigger and bigger and bigger near that number. Thoughts about that? The third case that it says right there is that the function might oscillate as it approaches a number. And so that's what's being shown, right? So number 3, the function oscillates as x approaches c. That's what's happening down here. Number 3 is that one. So when I graph sine of 1 over x, right? When you get close to 0 here, you're going to get close dividing by 0. And so this graph, when you graph it, it like oscillates, but as you get closer to 0, the oscillations get closer and closer together. And if you actually plot this on Wolfram, right around 0, it looks like this. It just goes crazy right around 0. And then it starts to spread out again past it, right? Because really close to 0, you're getting close to dividing by 0. And so it just goes crazy in the middle there. And I know I'm just kind of scribbling, but it really, if you look at the picture, it looks just like that. And so as we approach 0 on this one, it just oscillates out of control. So since sine of 1 over x oscillates as x approaches 0, the limit won't exist there. And I would encourage you to plot that one on Wolfram. If I had a little more time, I'd pull it up, but it looks a lot like that. There's kind of a fourth example that it's kind of like it almost doesn't even apply, which is why I didn't put it in the list. It's like if the function doesn't even exist at a point, then it's not even worth talking about, right? So for example, let me just bring the definition up again. In order for the limit to exist, the right-hand limit and the left-hand limit both need to exist and equal the same number. So let me show an example of one that doesn't do that. The limit as x approaches 0 of ln, natural log. So if you remember, again, back to pre-calc, natural log looks like this. And if we approach 0 from the right, it goes down to negative infinity, so that violates number 2. And if we approach 0 from the left, there's not even any graph over here to walk along, right? And so what I'm trying to point out here is a couple things, is that natural log is undefined for negative numbers, right? You can't plug negative numbers into logs. And so that means if we tried to look at the left-hand limit at 0, we can't even plug numbers in to begin with, right? Thinking about making a table there wouldn't even make sense. And so if we need both the left and the right-hand limits to exist, and one of them doesn't even exist to begin with, we can't even talk about the limit, right? So let me sort of write that home. And so I'll also add, if we approach 0 from the right, it goes to infinity, negative infinity. So it also doesn't exist. So both the left-hand and the right-hand limit have issues. So the left-hand limit and the right-hand limit don't exist. So the limit itself doesn't exist or can't exist. So this, as people finish writing, I'm just kind of summarize what I think we've done this period, is introduce the concept or the definition of a limit, which involves left and right hand limits, sort of talked about that notation. We showed some simple limits that do exist. We talked about how to estimate them using tables and graphs. And then I'm trying to drive the point home on this page by talking about some limits that don't exist. And it all has to do with either the left-hand limit and or the right-hand limit either not existing or not being equal to each other. That's really important, right? I'll just kind of go back to that definition one more time because I'll be going back to it a lot, I think. If we want the limit to exist, we need the left-hand limit and the right-hand limit to both equal L. And so that means it needs to exist, number one, and number two, it needs to be the same number, right? So chat thing, let me pull the chat up.